Hello, my name is Navid Zobeiry, and I'm an associate professor at the University of Washington. Today, I'm very excited to share with you a course that I have recently developed on physics-informed machine learning. Before getting into the content of the course and what we are covering and what you're going to learn, let me explain to you what physics-informed machine learning is with a simple example. Remember these fun experiments that you've probably done when you were a child? Growing rock candy crystals at home, taking a jar, mixing water and sugar, and then waiting for the crystal to grow. If you have done that, you realize that it's a very difficult thing to do over and over. So you can do it a couple of times, but it's challenging to do it many, many times, which means that the cost to do these experiments is not cheap. It's a high experimental cost. So if you have done that, let's say you're trying to predict the size of the crystal, the shape of the crystals an hour from now. This is a physical experiments, and you're trying to predict an outcome of the experiments. And let's say you're trying to develop a model, in this case, training a machine learning model that can predict the size of the crystal as time goes by. You can gather your data from the limited experiments you have done, and you can pick a machine learning algorithm trying to predict the size of the crystal as time goes by. If you don't want to let the machine learning model know what physics you're doing, it's the simple of gathering data and then feeding it to the machine learning model. And it has some limitation, especially when you're considering the size of this data and the complexity of what you're trying to predict. There's lots of underlying physics. Typically, there are multiple physical phenomena that are competing together, and it makes it quite challenging to properly gather data for that training. Would it be better if there was a way to let these algorithms know about the underlying physics to make them succeed with limited data sets that they have? And this is the whole premise of physics-informed machine learning. And you want to see, as we go through this course, the limitations of traditional machine learning models, how to take the underlying physics and feed it to the algorithm to create an enhanced version of the algorithm, which is the physics-informed. And there are quite a few different techniques as you're going to learn in this course. Okay, so let me clean this as I go forward through these slides. All the slides in this course, plus all the additional Python codes that I have developed for the course, are provided to you in the website that is written here, composites.uw.edu/AI. And you're more than welcome to share the slides and codes with others as well. So first, let's explain what we're trying to do. And in order to explain what we're trying to do, let's explain where the data comes from. There is a physics that we're trying to understand. It could be any types of physics. It could be any experiments we're trying to do. You might have two components that you're putting a glue between them, and you're bonding them together, and you want to understand the strength of the bond. You might be doing 3D printing, and you want to understand the quality of the end product, and so on and so forth. So there's some governing physics in the examples that you are interested in. In order to understand the governing physics, you might do some experiments. And these experiments give you some ideas, and as time goes by, you get more and more information about that specific physics. For example, if you look at the fluid mechanics, throughout hundreds of years of studies that we have done, we started to learn some high-level correlations in the data. For example, Reynolds number in fluid dynamics, which is a non-dimensional number, comes from the components of the experiments, including viscosity and length and speed, gives you something, gives you an understanding, high-level understanding about that problem. So you might come up with some correlations after doing experiments. If I increase the speed of 3D printing, my properties are going down. So that's high-level understanding comes from the experiments. Or you might be able to even present them using closed-form equations. So you go from a given experiment, governing physics, to some experiments, to some higher-level correlations. As time goes by, you might be able to develop governing equation for that problem. These are typically partial differential equations derived based on the conservation of mass, momentum, or energy. But overall, they represent a change in the system, typically as time goes by or as you change spatially through an XYZ domain. And eventually, we will take those closed form partial differential equation and we try to solve them using different numerical techniques. It could be a finite difference, could be a finite element, could be finite volume, or other methods. Throughout any of these boxes that I have here, you get some sort of information. Some of the information is in the data form that can be used to train a machine learning model, which means that it can feed into an algorithm such that it can predict the outcome of those tests. Typically, the traditional way we are doing machine learning is either we take the experimental data directly and feed it to a machine learning algorithm, or you might be able to take, if you have this last column, you might be able to take the boxes that are the numerical data. So you can run simulations over and over and over again, so like a virtual test, get the data and feed it to the traditional machine learning algorithm to predict the outcome. So we call this traditional machine learning model because this is just simple data fitting. The machine learning algorithm necessarily doesn't know what is the underlying physics, especially if you have limited data. If you have done 100 tests, it's very different than if you have 1 million data points. But the machine learning can understand true correlations underlying the data. The physics-informed machine learning tries to embed 2 more components into this mix. Either those correlations that are explained, like non-dimensional numbers, like Reynolds number, or other types of correlations, like the trade-off between temperature and concentration for rock candy formation, and feed that to machine learning algorithm as a high-level understanding. Or directly taking differential equation, use them to generate data to train machine learning models. So throughout this course, I'm going to do an overview of what are the main traditional machine learning algorithms, specifically for a regression problem, which means that you have done some experiments and you want to predict an outcome. And you're going to see a step-by-step how we can enhance that to create a physics-informed approach. Okay, so beyond the simple introduction that we're going to have in the next couple of lectures, which we're going to go over traditional and main machine learning algorithms that you might use in a physical system. There are 4 case studies that have been developed, which are case studies plus Python codes that you can go over the Python codes and you can exercise them yourself. And every case study is a different physical problem. We're going to use a different baseline machine learning algorithm to solve it. And then we're going to use different physics-informed techniques to enhance that process. So let me go over these 4 case studies. Every case study becomes either 1 or a few lectures. The first one, which is a longer one, is heat transfer problem. So in many scientific engineering problems, you are placing components, a part inside a convection oven or an autoclave, and you're heating it up. So there's a heat transfer that is happening. The heat goes through the air and goes through, let's say, a supporting tool into a given part. And that exchange of heat affects how the part temperature is set. So in this case, let's say we are trying to predict what is the temperature of this part after a given time, or what's the maximum temperature of this part. And to do this, we are going to first train a machine learning model, which is a neural network in this case. And you're going to see the limitations of that, especially when you have a limited number of data points. And then we're going to enhance it using different physics-informed approaches. This is the longest case study that you're going to see. The second one is related to that rock candy formation, or in general, if you have kinetics that you want to understand. As time goes by, how fast chemical reactions are happening, like diffusion in this case, or the rock candy crystal formation in the first case. In this example, limited experiments have been done, and we are trying to look at the data and come up with the closed form equation that describe the data. So it's basically going from experiments to some data to a closed form equation. And that's a very important application of machine learning approaches is not just fitting, they can actually come up with closed form equation that represents the underlying governing equation. So in this case, we're going to use a very specific approach called sparse identification of nonlinear dynamics, or SIND, which I am going to explain briefly in this course, but there are more information of that with my colleague Steve Brunter under the YouTube channel Ike and Steve. So these are the first two case studies, and again, for each of these case studies, you will have slides accessible on my website, and also the Python codes that have been developed specifically for that example, so you can see how the implementation works. Case study number 3 is related to 3D printing. So if you have done 3D printing, if you know about 3D printing, the process typically looks like this. You have a polymer, let's say thermoplastic polymer, that you're melting through an extruder, and you are depositing layer by layer onto a surface. So this is a specifically fused deposition molding, or FDM additive manufacturing approach. So in this case, there are multiple physics. There is the heat transfer. There's this melt solidification. When the thermoplastic is flowing, there is a fluid, viscous flow that is happening, and all of these are interacting to affect the end part quality. So in this case, we want to understand if you change the parameters of 3D printing, what's going to happen to the quality of the part, and specifically its strength. And I'm going to do this again, similar to other examples. First, we're going to develop a baseline traditional machine learning model, which in this case is an ensemble method, or different types of machine learning approaches. Including bagging and boosting, which are subcategory and ensemble methods. And then we're going to see how we can enrich that experience by letting the machine learning model know what is the underlying physics. In terms of the components, or what the physics that are interacting with each other, this is the most complex example because it has a few different types of physics that there are trade-offs between them. The last case study we're going to see is an adhesive failure. In many applications, you have to bond different pieces together, whether it's like your cars, whether it's like an aircraft, it's your watch, it's your laptop. There are components that you have to glue together. In order to understand the behavior of these components, you have to do some ASTM standard tests, in this case like shear tests, to characterize the strengths of these materials. In this case, with the few tests that has been done, we want to predict the strengths of the adhesive. And in this case, we're going to use a very specific type of machine learning approach, which is a probabilistic machine learning approach called Gaussian process regression, or GPR. And then once we applied GPR, and you learn what GPR is, we're going to enhance it by infusing physics into the training process. So 4 case studies. In every case, you will learn about the physics. You will learn about the baseline machine learning model that we're going to use. And you're going to learn how to enhance it by letting you know about the underlying physics. So overall, we are going to go through several different traditional machine learning approaches, which I'm going to cover briefly some of them in this introduction. And then when we go to the actual cases, we're going to look at the Python codes together as well. But there are Python codes provided for all of these in the introduction section, which I'm not going to go into details of the Python codes, but you can see the results of running those Python codes, and then you can run them yourself. So I've divided them into 3 different categories. Whether it's a good approach or not, it basically shows the different methods that you're going to learn if you don't know them, or it's like a reviewing of those methods if you already applied them before. So there are deterministic regression, and we start with a very simple case, which is linear data fitting. Then we go into more advanced method called decision trees, which is a bunch of decisions that divides the direction of the outcome, and we're going to explain that briefly in this introduction. I mentioned SIND and I mentioned neural networks, the 2 methods that you're going to learn. Gaussian process regression is a probabilistic machine learning, which is very different than this deterministic machine learning approaches. And explain the difference between two in the next slide. And then finally, ensemble methods, which are bagging and boosting techniques. And we're going to use that for the 3D printing case study. And specifically under bagging methods, you're going to learn about random forest. And on the boosting methods, you're going to learn about the gradient boosting machine and XGB regressor. So on the physics-informed machine learning approaches, which is the adds-on to these traditional approaches, you're going to learn many different techniques. But I have highlighted 3 different main techniques that you're going to see in this course. The first one, the first technique is physics-informed domain transformation. And it's basically if there are competing physics in your problem, can you get the initial inputs and output and transform them based on the underlying physics, and then do the training of the machine learning in that transformed domain, because the transformed domain implies some correlations that you already know. That's one of the most effective approaches, as you will see, and we're going to use that in a couple of examples. 2 are physics-informed features and parameters. And you can see this in a simple example. If you have a bunch of data sets, and in this case it's an X and a Z that you are changing X and you're measuring Z, and you're going to do a data fitting. If you have understanding higher level of the shape of these surfaces you're trying to predict, you can let the machine learning model know about those. Or the physics-informed features, if you can divide your machine learning models into areas which each is going to take care of one type of physics, and they come together, sometimes that becomes a lot more effective than pure data fitting. The last one, which is a widely used method in literature, is called physics-informed loss. And I want to explain to you what loss is and how we can enrich it with physics. But basically, when you're training any of these machine learning models, you have to minimize an error function. We call it loss function, which again, I'm going to explain in more details. So there is a traditional way we're defining it, which is the summation of errors, and we're trying to minimize that when you're training machine learning model. And you can add a physical parameter here to basically penalize the machine learning model if it doesn't capture the physics properly. And that's those correlations that you already know, and you are enforcing them by enriching the loss function. And if you're not familiar with any of these things, I'm going to go slowly through all of these things. First, I'm going to slowly introduce the baseline machine learning model, and then you're going to see how the machine learning model becomes more enhanced by putting physics in it. And for all of these, there are Python codes. And again, I'm going to go into details of the Python codes when we get to case studies. But in the introduction, I'm just going to go quickly over the results of these Python codes. But all are available to you for free. OK, so I have 2 more slides here to conclude this first lecture, which is an introduction to this topic. I mentioned this at the beginning. In many physical problems we're dealing with, we have small data. It's very difficult, it's very challenging, it's very expensive to generate large amount of data. So when you're doing machine learning with just 10 points, 100 points, 1,000 points, it's very different when you are training, for example, large language models on billions of data points. It requires you to do some advanced techniques. So that's why we have to use some of these algorithms with small data sets. But why is it that we can't typically use traditional machine learning models with these small data sets? This is a perfect example coming from literature. Imagine you have done a test where you are varying X parameter and you're measuring the Z value again, but you have only done a few tests. So these are all the circles you have seen here, you see here. And then you're trying to fit a machine learning model to predict the behavior. First of all, the experimental data is typically quite noisy. So you would have, if you do repeats in certain areas, you might see trends which are not realistic. It's just the noise in that area. And then sometimes you have outliers. So some of the tests might be just completely wrong. So you want to eliminate those from your test results. So small data sets, which is noisy, and there might be error in some of those data. And then imagine you want to extrapolate that and understand what's happening a bit further away from the area of data. If I ask you, I want to do a test where I'm changing the x value in this area where there is no experiments, what's the prediction of this machine learning model? Then there is not much there's not much you can say about that predictions. This is what sometimes we call brittle AI. Sometimes you might say the AI is hallucinating. It's basically could be any of the lines that you extrapolate outside of the data. If you don't know anything about the physics, any of them can be right or none of them can be right. But it could be that there is one that is actually the correct extrapolation. And if you let the training model know about the correlations, it can capture that. And that is the essence of the case study number 1 on heat transfer that we're going to learn. We're going to see how effective these techniques are to capture well beyond the original training zone. So beyond a small data set, you might say that there are some experimental results that you have that are not small, but you have a lot more data. And that opens up rooms for other techniques as well. But where do you get large experiments from physical problems? And there could be 4 different sources of large data. You might be running a factory where there are lots of automation in the factory, and you're building a lot of components very fast. And every time you're building a component, you're measuring things, inputs and outputs. Then you will have a large data sets. So that opens up different areas. But even if you're in that domain, you might think that you have large data sets, but running those experiments, especially as the parts become more complex, becomes very challenging. You might have high throughput testing, automated testing that you are doing things over and over again in an automated way. You need to have a large data sets. You might have simulation, and again, I mentioned you can run simulation many times, even though some simulations are expensive to run. As the fidelity of simulation goes up, you have to spend more time, and there's more cost associated with running them. But sometimes you can get lucky to understand part of the physics through simulations. And then lastly, from every test you're doing, rather just gathering one data point, sometimes you might gather an image or time series. Things are changing as time goes by. Then it's a rich data set. So it's an image, but every pixel in the image can be a data point. Any of these areas can give you a large data set. And if you're not within these domains, most likely you're in the small data sets. Even for some of these things, you might think that you have a large data set, but running the experiments in a way that you're changing the inputs in a meaningful way and measuring the outcome, the things that you want to measure, is not straightforward in physical system. So hence, many of the techniques we're going to learn here becomes useful even in these cases. I'm going to conclude the introduction here, and in the next section of introduction, we're going to go over some basic machine learning approaches.